Hi guys, and welcome to the first video for 7 Steps to a 7 in Olympiad Geometry. This course will cover the most fundamental ideas for solving Olympiad geometry problems, ranging from familiar concepts like angle chasing to more sophisticated ones like radical axes. Before we get started, I want to say that this course is not intended to be comprehensive. In fact, there is so much more to Olympiad geometry than what I will be covering in this course, such as projective geometry and inversion. Rather, I intend for this course to be like a bridge between expected theory and computational level concepts, so for example the AMY, to Olympiad math, where I cover the basics and provide intuition for these geometry problems. So this way, when you see a geometry problem as the first problem on your Olympiad that you may be taking, you have a good shot at solving it. You won't be listless like, what do I do? And yes, I'm assuming that you're reasonably comfortable getting close to qualifying for your country's National Math Olympiad. And for those of you in the United States, this is equivalent to around a 6 on the AMY. If you aren't any of these, then that's completely fine. But the only thing I don't want that to happen is for you to try learning material that you aren't ready to learn yet. Because if you aren't comfortable qualifying for your country's National Olympiad or not close to qualifying for AMY, then the concept in this course may be confusing to you, and you'll only leave this course more confused than you were before. And I don't want that to happen. I want you to start learning the material when you are ready to learn it. All right, enough said, let's get right into the course. Enjoy. So we'll be starting off with some facts that you probably already know. So for example, let's prove that inside a triangle that the sum of angles is equal to 180 degrees. All right, so how do we start this problem? Well, the first thing that we need to do in any geometry problem that you do, whether it be IMO problem 3 or JMO problem 1, one of the easiest problems, is always draw a diagram. This is the most important step in any geometry problem. Once you draw a diagram, you get a good understanding of what exactly you need to prove and what exactly is happening in the problem. So in this case, the diagram is just drawing a triangle and then possibly marking each of its angles. Okay, now that we've drawn our diagram, what is the next step? It seems like we're stuck right now, but let's think of what else could be equal to 180 degrees. And if we think for a bit, we realize that a 180 degrees is just the angle measure of a line. So if we could rearrange these three angles to form a line somehow, then we would be done because the measure of a line is 180 degrees. So we want one of these lines to pass through a vertex because then we have one of these angles situated. So we can, for example, draw this. Then here we want this angle plus this angle to be this angle plus this angle here. Because if these two angles have the same sum as these two, then we just add this one to finish. And this would just make it simpler if these two angles were just these two angles down here. So for example, if we have this one here, then this is that angle here, and this is that angle over here. But then we realize that this condition is equivalent to this line being parallel to this side down here. And that means that we can finish the problem. The two angles here are equal, and so are these two angles down here. Erase that. So these two angles over here are equal, and those two angles are here. And obviously this angle is equal to itself. So the sum of the angles in this triangle is equal to the sum of the angles on this line, which is 180 degrees. Right. So this is basically the main idea of how geometry proofs work. And the main idea is that we want to start off from what we already know and then use those to our advantage. And this will be a recurring theme throughout Olympiad geometry, where you start with some concepts you know and use them to build new concepts, which build up new concepts, newer concepts, and then they can solve harder problems. All right, let's take a look at another theorem that you may know. So O is the center of a circle, and A and B are points on the circle. And suppose that C is a point on major arc AB. We want to prove that the measure of angle AOB is 2 times the measure of angle ACB. So what is the first step in this problem? Well, you may think it's some sort of angle chase with the sum of angles equal to 180, but nope, it's drawing the diagram, as I said earlier. This should be the first step in any geometry problem you solve. So let's draw the diagram. So if we draw like so, that's our circle, this is our center, then these can be our 2 points A and B. And then we can set our point C to be up here. Then angle ACB is over here, and angle AOB is over here. We want to prove that this angle here has twice the measure of this angle here. Okay, so what can we do now? Like, how do we deal with the point C? Well, we know it lies on the circle, so by definition of a circle, this would mean that CO is equal to both the lengths AO and BO, because, well, a circle is just the set of points which are a certain distance from the center. So this motivates us drawing the line CO over here. Then each of these lines are equal. So now let's see what we have here. Well, we know that these two lines are equal, these two segments. So that means that AOC is isosceles. So that means that we can let this measure here be some sort of angle. Let's call it A. Then this is also A. So by sum of the angles in the triangle, which we proved earlier, it is 180 minus 2A. And if this is B, then this one here is 180 degrees minus 2B. And now we can finish. If we look at this angle AOB, we can relate it to these other ones by using a 360-degree rotation, because the sum of these three angles here is 360 degrees by default. So that means that we have 180 degrees minus 2A plus 180 degrees minus 2B plus the angle AOB is equal to 360 degrees. And if we solve it, we get angle AOB is equal to 2A plus 2B. And now we need to prove that this is twice angle ACB, which is 2 times A plus B. But this is just clear. We just expand both sides and we are done. Or are we? It turns out that if you're careful, then there's a mistake in the above proof. Then because we're assuming the fact that O lies inside the triangle ABC, because that way we can do things with these isosceles triangles and we have A plus B. But what if O lies outside? For example, C can lie here, and then we have something weird going on. Well, it turns out that the theorem still holds in this case, and I'm going to leave it to you to prove it. So prove it on your own. And it's very similar to the proof I gave here. But the point is that you have to be careful when doing these things, because you never know what configuration issues you can come into. Because given a certain geometry statement, there are several different configuration issues that can arise. And this is one of them, for instance. Next week, we'll figure out a way to deal with many of these configuration issues, most if not all of them. But for now, we're just going to be dealing with every configuration that we see. Now we can solve our first example. And here it is. Inside an acute triangle ABC, the point D is the foot of the altitude from A to BC, and O is the circumcenter of the triangle, meaning that O is the center of a circle containing all of A, B, and C. Prove that the two angles BAD and CAO are equal. So once again, our first order of action is to draw a diagram. And let's draw it as follows. So we have our point A up here, then our point B and C down here. So here are B and C. Now the point D is just a foot of the altitude, so it's down here. And the point O is the center of the circle containing A, B, and C. So we would expect it to be equidistant from A, B, and C. So maybe it should be around here. And the goal is to prove that these two angles are equal. All right, so motivated by our discussion in the previous example with the inscribed angle theorem, which is what it's called, we can draw this line here and use that theorem here. So if we call this angle B here, then we know that this is equal to 2 times angle B. And then by the sum of angles in a triangle, we know that this is equal to 180 minus 2b over 2. Because these two angles here are equal, and when we add them and add 2b, we must get 180. So that means that this is equal to 90 minus b here. So we have to show that this is also equal to 90 minus b. But then the only piece of information that we haven't used yet is that d is the foot of the altitude. So that means that this angle here is 90 degrees. And now we can look at the triangle ABD, because that's how we incorporate D when we have a right angle here. So if we use the sum of angles, we get B plus 90 plus angle BAD, so we want to prove that, is equal to 180 degrees. And when we solve for BAD, we get BAD is equal to 90 minus B. And this is conveniently equal to CAO, and this solves our example. So the point is that we want to figure out how each of these points can relate to the rest of the diagram. Because when we do that, we're able to get an idea of what we should do. In this case, with the circumcenter, we introduce the isosceles triangle, and then we use the sum of angles in a right triangle to get that the two angles we needed were equal. All right, so now what? Well, the inscribed angle theorem is not powerful enough to do anything on its own. But you may have noticed that theorem 1.2 should apply in general. If you have these 2 points A and B and another point C, that means that if you vary C along this arc here, so it could be any of these points, all of these angles here are the same. And this is the part where we can use things to our advantage. And we're going to be discussing that shortly. We can extend the notion of the inscribed angle theorem by using the most important technique inside angle chasing, which is called cyclic quadrilaterals. So what exactly is a cyclic quadrilateral? Well, it is just a quadrilateral ABCD where all the points lie on a circle. So let me go ahead and draw an example for you. So if we have our circle here, then this is A, this is B, this is C, this is D. This quadrilateral here is cyclic. So we want to figure out what is so special about these cyclic quadrilaterals. Well, as it turns out, they all satisfy several nice angle conditions. The first one is that angle BAC is equal to angle BDC, and angle ADB is equal to angle ACB. And we just continue going around the quadrilateral. So we have angle ACD equals angle ABD, and angle CBD equals angle CAD. And we also have an extra pair. So we have angle BAD plus angle BCD is equal to 180 degrees. So how do we prove all of these? Well, normally the first step would be to construct a diagram, but I constructed one for you when demonstrating what a cyclic quadrilateral was. So consider yourself lucky. So how do we prove this first? Well, if we take a closer look, we notice that this is just the inscribed angle theorem that we proved earlier, because they're twice the angle of, if this is the center O, they're twice angle BOC. No, more like 1/2 of angle BOC, because BOC is twice of those angles. So that means that each of these guys are dealt with. So how do we prove that angle BAD plus angle BCD is equal to 180 degrees? Well, we know that A and C lie on different sides of BD, so one of them lies on the major arc and the other lies on the minor arc. Let's suppose that C is the one that lies on the major arc, so that we know that angle BCD is equal to 1/2 angle BOD by the inscribed angle theorem. Now, what about BAD? Then we want to prove that it is 180 minus this. Well, why not just use the inscribed angle theorem again? Well, we can't exactly do that because A is not on the right side, but we can repeat the similar argument for its proof by drawing the isosceles triangles. And when we do that, we discover that BAD is equal to 180 degrees minus 1/2 angle BOD. And then by adding these two, we end up proving our result. So therefore, the cyclic quadrilaterals satisfy all of these nice properties with these angles. All right, cool. But how do we prove that quadrilaterals are cyclic? Because after all, if we don't have any cyclic quadrilaterals given to us in a problem statement, we can't really do much at all. So how do we prove a quadrilateral is cyclic? As it turns out, all of the angle equalities I gave earlier are actually reversible, as long as you're careful. So let's go ahead and consider a quadrilateral ABCD. So A, B, C, and D. And suppose that we know that angle ABD is equal to angle ACD. Must it follow that this quadrilateral is cyclic? Well, yes, it must, because suppose that we construct the circumcircle triangle BAD. Now, here's a cool technique we can apply. First, we can intersect AC with the circle again. Suppose that it's a point C prime. Because if C is not on the circle, then at least C prime is. And we can work with that. Then this means that if we draw this, by the inscribed angle theorem, this is also equal to angle ABD, which is equal to angle ACD. So therefore, angle ACD is equal to angle AC prime D. And if we angle chase a bit, and on this line AC prime, we get that angle CC prime D plus angle CC plus angle C prime CD is equal to 180 degrees. But you might know that this causes an issue, because the sum of the angles in a triangle is 180 degrees, so this has to be 0 degrees, which is absurd, right? Because that would mean that C is equal to C prime. And therefore, in fact, C does lie on the circle. So this proves that these angle equalities are actually reversible, in that one of them implies that the quadrilateral is cyclic. And this idea of proving this is known as phantom points, where we want to prove something, then we can find a point that satisfies that condition and prove that our 2 points are the same, like in this case C equals C prime. And I'll leave the other cases up to you, like the proof that angle ABC plus angle ADC equals 180 degrees implies that ABCD is cyclic. I'll leave that up to you to figure out. All of the cases very identical to this one. But you must be careful here, because if the points are not in order, suppose that this is A and this is D, then B, then C down here. Then these two angles can be the same, but the quadrilateral is not cyclic. C and B have to lie on the same side of each other as AD. We'll figure out a way to resolve this in the next video, but for now we just have to be very careful about configurations. This introduces a pretty nice philosophy involving cyclic quadrilaterals. Suppose that you want to prove that if you have points A, B, C, and D, that these two angles here are equal. Well, this amounts to proving that the quadrilateral ABCD is cyclic by the inscribed angle theorem. But then if we show that these two angles are equal, then we are done, because these two angles are equal implies this quadrilateral is cyclic, and we get these two angles are equal from here. So, and often this goes over many steps. So we prove that one quadrilateral is cyclic, use that to get two more angles that result in another cyclic quadrilateral, and this process keeps going until you get what you want. So with that said, let's take a look at our first example. So the example goes as follows. So let ABCD be a square, and let O be the center of it. Let E be such that, suppose that E is outside of the square such that angle AEB is equal to 90 degrees. What is the measure of angle AEO? All right, so the first step in any geometry problem is to draw the diagram. So let's do that. So we have our square ABCD, and O is the center, where it's the intersection of the diagonals. And we have a point E up here such that this is 90. And we want to find the measure of this angle. All right, so first we want to figure out how to introduce O into this picture. Well, as I said earlier, the main property about O is that it is the intersection of the diagonals. And the diagonals in a square are perpendicular, because that's one of the defining characteristics of a square. Otherwise, if they weren't perpendicular, then it could be a rectangle. So we know that this is 90 degrees, 90 degrees, 90 degrees, 90 degrees. All right, so now that we figured out how to deal with point O, let's figure out what we know about point E. Well, the only thing we really know is that angle AEB equals 90, which is given to us already. So how can we use this? We want to find some angle that has A something B, and that's also 90 degrees. So that way we can probably get a cyclic quadrilateral. But that point can just be O. So angle AEB plus angle AOB is equal to 90 degrees. And therefore, this quadrilateral AEBO is cyclic. So AEBO is cyclic. And to finish, we have angle AEO is equal to angle ABO by our cyclic quadrilaterals. So now we've just gotten rid of point E entirely from the question, and we just have to figure out what this angle is. But this is just half of 90 degrees, which is 45 degrees. So let's give a recap. So we used what we knew about the points O and E to find a cyclic quadrilateral. And using those, we could decipher information about the line EO by using the inscribed angle theorem on the circle that we discovered. All right, let's take a look at an example problem that encapsulates everything that we've discussed today. So here's the problem. Let O, A, and B be points on a line L in that order. Let P be a point on the circle with diameter AB. The line PA meets the line through O perpendicular to L at point Q. And the goal is to prove that BQP is equal to the angle BOP. At this point, I recommend that you pause the video right now and try the problem on your own. Because if I only give you the solutions all the time, you won't be learning anything. So yeah, please pause the video right now if you haven't already and try the problem on your own. When you're ready to look at the solution and discuss it with me, click the play button. Okay, so let's discuss this problem now. So the first step is to create a diagram. So we have points O, A, and B on a line in this order. So O, A, and B, suppose. So this is the line L. And P is a point on the circle with diameter AB. So we have something like that. And P is over here. And the line PA meets the line through O perpendicular to L at point Q. So this is a line perpendicular to L at O, and this is the line PA. Or this is the line PA. And it intersects here at Q. And the goal is to prove that angle PQP is equal to angle BOP. So how do we get started? Well, we want to prove that these two angles are equal, and given the style of this problem statement, it really calls for us to prove that BPOQ cyclic. This is what we want to prove, because if we prove this, then we're done by the inscribed angle theorem. Okay, so how can we prove this exactly? Well, we want to find some pair of subtending angles that are equal. So how do we do that? Well, one thing that we haven't used yet is that the line is perpendicular to L here. OQ is perpendicular to L. So that means that we have that this angle is right angle. So QOB is 90 degrees. So if we can prove that QPB is 90 degrees as well, then we are done. So is this a 90-degree angle? Well, QPB is just angle APB because A lies on PQ. That's the other part of the problem we haven't used. So we want to prove that angle APB is 90 degrees. And we haven't used the fact that P lies on the circle with diameter AB yet. And therefore, by Thales' theorem, this is 90 degrees. So that means that QOB is QPB, so the quadrilateral is cyclic, and we are done. And here's what a very concisely written proof would look like. Because angle APB equals angle QPB equals angle QOB equals 90 degrees, we know that BPOQ cyclic. Thus, we have angle BQP equals angle BOP as needed. So the main idea is, again, we find a cyclic quadrilateral that we want to prove. And then with that, we end up proving that cyclic quadrilateral is true in a different way by using different subtending angles, in this case with the 90-degree angles. All right, so that's one of the main examples we're looking at. I've included a bunch of exercises inside the corresponding handout for this video, which is linked in the description of the video. And I highly suggest you work through those on your own. I'll be providing help in the comments, so if you need a hint on the video, please leave a comment on the video and I'll be happy to give more hints. All right, thank you so much for watching this first video, and I'll see you in the next one.